Welcome back to the class on HVDC transmission system. In this lecture, we are going to study the apparatus requirement for the HVDC system. Not only that, DC links also we are going to discuss in this. This is the overall block diagram of HVDC system. This is the AC bus. This is the transformer. This is the rectifier station. By means of this rectifier station, we are converting the AC power into the DC power. This is the smoothing inductor. Here we are keeping the DC filter. The power will be transmitted through the DC transmission line. These are the DC transmission line. Again, inverter station. Where we want to use the electrical power, again we have to reconvert into the DC power into the AC power. This is the station transformer controller. This controller will be generating a firing pulse to the SCRs in an inverter station. This controller also will be generating a firing pulse to the SCRs in a rectifier station. This is the AC filter. Due to the operation of the rectifier station, the some amount of harmonics will be generated in DC side as well as AC side. Those harmonics will be filtered by using a AC filter. See here we are using a DC filter to reduce the harmonics in a DC voltage. The main purpose of the smoothing inductor is to smooth the DC current. These are the different main parts in a HVDC system. Now we are going to see what are the different types of HVDC links are available practically, that we are going to see. Whenever we are interconnecting two networks, we are going for the DC link or AC link. But here we have so many advantages in a HVDC links. So here we are going to study the different types of HVDC link. There are three different types of HVDC links are available. One is monopolar link, bipolar link, homopolar link. Now we are going to see one by one. Monopolar link. In a monopolar link, only one conductor is there. Through that conductor, the power will be transmitted. The polarity of that conductor is negative polarity. The current will be taking a path through the ground in this manner. This is one pole, this is another pole. At each pole, this is sending pole, this is the receiving end pole. See, at the sending end pole, one converter is there, receiving end pole, one more converter is there. These are the transformers. It has a disadvantage because the current is taking a return path through the ground. So, because of this disadvantage, we are not going to use the monopolar link practically outside. But here, we are keeping a ground here. At every pole, we are making a ground. This is the grounding. Generally, the grounding will be taking place 15 to 50 kilometers from this pole. Next, we are going to see the bipolar link. In case of bipolar link, the two conductors are there. One is positive conductor, another one is the negative conductor. Now here, at each pole, the two converters are there. This is one converter, this is another converter. The same manner here, this is one converter, this is another converter. Suppose here, this converter is operating, it will be taking a current in this direction. Now, the lower converters are operating, it will take a current in this direction. The midpoint at a DC side, at a rectifier station as well as inverter station, that is grounded here. The potential of this ground is half of the potential of this conductor. Generally, we are using this type of bipolar link practically outside because it has more advantages. If this converter is not operating, we can transmit a power through the lower converters. If the rating of the conductor matches the full load current rate, so the reliability of the system is more. So we are using these converters practically outside. Homopolar link. It is almost all equal to the bipolar link, but the only thing is the current taken by each pole is negative in this direction. Now how this current is passing in between the converters means this current will be passing in this manner. This current will be taking a return path through the ground. This current will be taking a return path in this manner through the ground. It is almost all similar to the bipolar. Only thing is the direction of current, how it is taking a return path. The main advantage of the homopolar link is that each pole, this is one pole, this is another pole. These two poles are operating parallelly. So it is more economical when compared to the bipolar link. Next we are going to see the one more important component is the converter station. Here we have seen the two 12 pulse units per the pole. This is one pole. So at this pole, here we are using a 12 pulse converter. This is 6 pulse converter. This is 6 pulse converter. Both are connected in a series, which gives the 12 pulse converter. This is smoothing inductor. This is the DC filter. These are the transformers. See, if you observe this transformer, one transformer is connected in a star star, another transformer is connected in a star delta. These are the AC filters. This is the pole 1, this is the pole 2. At each pole, we have used the one 12 pulse converter at sending end and one more 12 pulse converter at a receiving end. So finally, we got the two 12 pulse converter per pole. Now we are going to see the 12 pulse converter. How you get the 12 pulse converter means two 3-phase converters are connected in series. We are getting the 12 pulse converter. One converter will be feeding with a star-star connection. Another converter will be feeding a power through the star-delta connection. This is the star, this is the delta connection. This is the star, this is also the star connection. See, if you observe here, this is the one 3-phase converter, this is another 3-phase converter. The practically how the valves are available means single valve. See, two valves are packed as a single valve. So double valves. See here, four valves, quadral valves. So in this manner, the practically the availability of the SCRs are the single valve, double valve, and quadral valves. Now we can use that valve and we can make the two 3-phase converters. Those 3-phase converters we have to connect it in series. We are getting the 12 pulse converter. The pulses are given individually to the each SCR based upon the requirement and comparing with the AC voltage to decrease the losses in a 12 pulse converter. We are using the different types of the coolings. One is air cooling, another one is oil cooling, and water cooling. Generally, we are using the ionized water for cooling of the SCR, which is giving the better efficiency for the converter. Nothing but it reduces the losses in a converter when it is carrying the full load current. Next, suppose if we want to on the SCR means we have to give the triggering pulse. Those triggering pulse will be generated at a somewhere at a ground potential that will be transmitted to the SCR through the fiber optic light guided system. At SCR, we are using a driver circuit. The driver circuit will be converting this ground potential to the electrical signal. Those electrical signal will be given to the SCR so that it will be on. If it is forward bias with a AC supply voltage. And this valves also will be protected by means of a snubber circuit, protective firing, and gapless surge arresters. Third important component is the converter transformers. Already we have seen in the block diagram at a rectifier station we are using a one transformer. At a inverter station also we are using a transformers. So how we are going to select this transformer means there are three different transformers we are using in HVDC system at a stations. One is 3-phase 2 windings. Nothing but a 3-phase windings we are keeping on a transformer at 2 windings. Single phase 3 windings. Suppose if you use a single phase winding, the type of windings we are using is 3 winding. Single phase 2 windings. How we are going to design this transformer means the valve side windings are connected in parallel with a neutral ground. So what are the windings which is giving a power to the valves in a converter? Those windings are connected in a parallel and the neutral point should be grounded. There is no point in neutral in a delta connection. Next, the leakage reactance of the winding are designed such a way that it can able to withstand the short circuit current of the SCRs or valves. When the converter is operating, there is some amount of DC voltage will be injected into the transformers as well as the DC side also. It has to design such a way that it can able to withstand the DC voltage stress, and it also will be increasing the eddy current losses due to the harmonic currents. So whenever the converter is operating, the some amount of DC voltage will be injected into the transformer. It may saturate the course of a transformer. When you are going to design a transformer, it should not be saturated. So these are the parameters what we have to consider when you are going to design a transformer which we are using in a HVDC converter station. Next, filters. We know that when the converters are operating, it is injecting a harmonics into the DC side as well as the AC side. So there are three types of filters are there. One is AC filter, another one is DC filter, third one is the high frequency. AC filter is nothing but it is using a passive circuit, nothing but an inductor and capacitor, which offers a low impedance to the harmonics. So the harmonic current will be bypassed through these components, and harmonics will be eliminated by means of a AC filter. Here, there different types of AC filters are there. One is tuned filter, nothing but we are tuning the frequency of filter to the frequency of harmonic, so that the particular filter will be filters the particular harmonic. And damped filter. These filters are designed for the band of frequency, so that those band of harmonics will be bypassed from the line. Next, DC filter. The DC filter also will be similar to the AC filter, but these filters we are using to eliminate the harmonics in a DC side of the converter. And high frequency filter. So whenever we are converting the AC voltage to DC side, due to the switching operation, a high frequency harmonics will be injected into the transformer that is coming towards the line. So we are using a high frequency filter between the line and the transformer, so that it can able to filter the high frequency harmonics which does not entering into the line. Reactive power sources. In AC transmission system, the transmission line requires a reactive power, but in case of a HVDC system, the transmission does not require a reactive power, because on a transmission line we are sending a DC power. But when the converter is operating, when the converter is converting the AC power to DC power, if the converter is carrying a 100% of real power, means it requires a 50 to 60% of the reactive power. The sum of the reactive power will be given by the AC filters which are connected in the AC side. Mostly that total reactive power does not be supplied with the AC filter. So we have to use the shunt capacitor, synchronous condensers, and static wire system to compensate the reactive power which is required to the converter. Smoothing reactor. When the AC power is converted to DC power, there is some amount of ripples will be existing on the DC side. To reduce the ripples in a DC current, we have to use the one large inductor, which is a linear reactor, which smooths the DC current. And DC switchgear. Whenever we want to interrupt the DC current in a DC side, then we have to go for the DC switchgears. Suppose if we have AC switchgears, means that AC switchgears we can modify and we can use it in DC switchgears, and also we can use the metal return transfer breaker MRTB. This is also will be developed nowadays. We can use these breakers to interrupt the DC current. In addition to all these apparatus, HVDC system requires a AC switchgears and associated equipment for the protection of the SCR and the station and a transformer, and also it requires a measurement part for the converter station for the effective protection of the overall HVDC system. So thank you very much for watching this video.